Hello. In this video, we're going to look at related rates, which is section 3.9. This is our first chance to actually solve some word problems involving calculus. If you've been wondering where the word problems are and where some of the practical applications of calculus are, well, you're in luck. We're going to take a look at some of those today. Now, to start off, we need a bit of a warm-up. We're going to do some just basic word problems that don't involve calculus. So let's look at this problem here. A ladder of length 5 meters leans against a wall. When the base is 4 meters from the wall, how high up the wall is the ladder? So I encourage you, pause the video, try to do some problem solving here. Think about this without calculus. You just need to solve this as a math problem. See if you can figure out how high up the wall the ladder is. So I'm assuming you gave it a try, and hopefully you have something like this. Well, there's a ladder, so let's see, maybe something like this. Here's your ladder, and there's a wall. So here's your wall, and I guess there's a ground too, right? So maybe we should draw the ground. Maybe it's got some grass on it. Who knows? You can make your picture as detailed as you want. Now, what information do we have? Well, the ladder is length 5, so that goes here, 5 meters. The base is 4 meters from the wall, so this is 4 meters over here. And we're asked to find how high up the wall the ladder is, so we're asked to find x. Well, if you take this picture, you can see pretty clearly that the wall and the ground, assuming this thing was constructed properly, make a right angle. So we have Pythagoras' theorem. A squared plus b squared must equal c squared. So 4 squared plus x squared equals 5 squared. Or 16 plus x squared equals 25. So x squared equals 25 minus 16. X squared equals 9. And x would equal technically plus or minus 3. But because you can't have a negative height for a wall, we obviously take the positive. So x equals 3 meters. And like all good word problems, we should answer in a sentence, how high up the wall is the ladder? So the ladder is 3 meters up the wall. So there we go. That's our solution to the word problem. Hopefully you came up with something like that. It's not a terribly complicated word problem, but the key, of course, is to be able to draw that picture, to translate from the math, English, to the math picture and the equation, right? Just because somebody gives you an English question here and they're talking about math doesn't mean you know what you're doing. There's a lot of words here. There's a lot. It's trying to say, what's the key piece? Maybe the 5, maybe the 4. You're trying to decode this and turn it into a picture and then into some type of equation. Now, let's try to do that again, but this time with some calculus. So here's your next problem. Now the ladder is moving. When the base is 4 meters from the wall and the height is decreasing at a rate of 2 meters per second, how fast is the base moving away from the wall? Wow, that's a bit of a trickier problem. Pause the video and see if you can make any progress. So I'm assuming you gave this a try, and maybe you got yourself an answer, maybe you didn't, but I'll show you at least the beginning of the setup. So the ladder is now moving. And now we're asked to find not a distance like before, but we're asked to find a speed. How fast is the base moving away from the wall? So if you ended up with a length, if you ended up with 3 meters or 4 meters or 5 meters, that's not correct because we're asked for a speed, a velocity, a change, if you will. Now the ladder is still the same distance as before, same length as before. We would have, this is our triangle, 5 meters for the ladder. But because the ladder's moving, it's not going to always be a distance 4 from the wall. If you imagine the ladder's going to be at lots of positions. First the ladder is maybe closer to the wall, and then the ladder gets further away from the wall, and then eventually the ladder is almost laying flat from the wall because it's sliding away. The ladder is going through each one of these situations. The ladder is moving away from the wall. And so it's not entirely fair to call the bottom 4 or 3 or any number. The bottom's moving. And so the bottom needs to have a variable, maybe x. And similarly, the top of the ladder is moving down the wall. So that's not going to be a constant number either. We need to give that a letter, maybe y. And so our equation is x squared plus y squared equals 5 squared, of course because of Pythagoras. And now we can't solve that equation for x and y. There's two variables. So this begins to become a little bit more complicated. How do you solve an equation for two variables? But we also want a fast, we want a rate. Maybe we should look at a derivative. Maybe we should take the derivative of this. It's not entirely clear, so we'll return to this problem in a few minutes. But first I want us to think about the derivative. So as a remark, every derivative represents the rate of change of the dependent variable with respect to the unit change in the independent variable. You might not have thought of a derivative like this before because you think of the derivative as the slope of the tangent, and that's correct. But slope measures change. It's the change in y or the change in x. So it represents a rate of change, a rate. So if we have, let's say, in this case, dv dt equals -3, well, in this case, we're going to say the bottom is t for time. It means that v, whatever our variable v is decreasing at a rate of 3 units for every unit of time because this is our slope, -3 or 3 over 1. That -3 over 1 means we have a rate of 3 and it's decreasing because it's negative. Or if we had dx dt equaling 7, it means x is increasing because it's positive at a rate of 7 units for every unit of time. So let's look at this question here. We have x squared plus y squared equals 25. And we're going to be told that dx dt is equal to 8. And we're going to find dy dt, where x is equal to 3 and y is equal to 4. Well, let's take a look at how we would solve this. We're looking for, in this case, a derivative, dy dt. We're given another derivative, dx dt, and we're given some information, x and y. Well, how do we solve this? How do we find dy dt? And the first thing we notice is that we have an equation, and we're looking for a derivative. So to find that derivative, we literally take the derivative of this equation. So if we're going to differentiate, we have to use implicit, so we get 2x. But be careful here. We're going to differentiate. We're going to differentiate not with respect to x, but we're going to do it with respect to t. Because we're not looking for dy dx. We're looking for dy dt. And because of that, we have to use implicit on both variables. We write dx dt because x is not going to be our variable that's, in this case, independent. X is going to be dependent on t. So we get a dx dt, and then we do 2y, our typical dy dt, equals, well, the derivative of 25 with respect to t is still 0. So we're actually using implicit on both variables because neither one of the variables is the t. If, though, just to help clarify this, if there was a y squared plus t squared at the end, the derivative of t squared would be 2t. But if you have an x or a y, because they're not t, the derivative of them is going to have this extra dx dt or this extra dy dt because of implicit. Okay, so we've done the derivative. Now we look and say we have some information. X is told to be 3, y is told to be 4, and dx dt over here is told to be 8. So let's plug in each one of those numbers. So for x we get 3, for dx dt we get 8, for y we get 4, and we'll put the other pieces of the equation down. We have 2 times x, so 2 goes in front there, plus 2 times y. And we don't know dy dt, so we'll leave that written down as an unknown. Well, we can simplify this a little bit. 2 times 3 will be 6, times 8 will be 48, plus 8 dy dt equals 0. So we can move 48 over to the other side, and we will get 8 dy dt equals negative 48. We can divide both sides by 8, and dy dt equals negative 48 over 8, which is negative 6. So we found dy dt. So how does this help us solve our original problem? Well, I'm going to show you a series of steps, and then we're going to redo that problem with the ladder and see if we can figure out how to solve it. So here's your series of steps. When you're solving a related rates question, here's what you're going to do. Step 1, you're going to draw a picture and label it. It's always a great idea to draw a picture. Pictures help us understand the English and interpret it in terms of math. Step 2, you're going to identify the rate you're looking for. So this might be, maybe you're looking for dx dt. Maybe that's what you're looking for. Or maybe you're looking for dy dt. You're looking for some rate, and you're going to identify what you're looking for. Then you're going to identify the information given. Maybe someone tells you x equals 3, or maybe someone tells you something about maybe dy dt is equal to something, maybe 4. Who knows? You're going to put in the information that you're given, or at least identify it. Then you're going to relate the variables with an equation. You need some type of equation. If you don't have an equation, there's nothing for step 5. Step 5 is when you're going to differentiate both sides of that equation. Step 6, you're going to substitute in all your information that you were given here into step 6. You'll solve for that rate you're looking for, and then step 7, of course, you'll answer in words. So let's try that ladder problem again. So now the ladder is moving. Again, remember we had the ladder is 5 meters long. When the base is 4 meters from the wall and the height is decreasing at a rate of 2 meters per second, how fast is the base moving away from the wall? So step 1, let's draw that picture. We have the ladder, we have the wall and the ground. The ladder is 5, but the wall is going to be a y and the ground is an x because the ladder's moving. And so the wall and the ground are never the same number. They're not constant, they're not fixed. They are varying, so they need variables. This is step 1, drawing a picture. Step 2, we need to identify the rate we're looking for. We're looking for how fast is the base moving away from the wall. That would be dx dt, the rate of x in terms of time. So how fast is it moving in meters per second? How fast is the base moving away from the wall? And this, we don't know. We don't know how fast it's moving. That's our question. Well, number 3, we should identify what information we're given. Well, we're given dy dt because we're told, actually, if you look here, we are told that the height is decreasing at a rate of 2 meters per second. So we're told that the change in y, the height is decreasing, so it's negative, 2 meters per second. We're also told, of course, that the base is 4 meters from the wall and that the ladder is 5 meters. We've included the 5 on the picture, but we're told that the base is going to be 4 meters from the wall. So we're told we're looking for the rate when looks like x is going to be equal to 4. Now the all-important equation, step 4, we need to come up with some equation that relates x, y, and 5. Now this equation isn't particularly challenging because we did it in the very first problem. We know Pythagoras is here to help. X squared plus y squared will equal 5 squared. Alright, let's go ahead and take the derivative. So 2x dx dt plus 2y dy dt equals 0. So on to step 6. We want to start plugging in all the information we have. Well, we know x is 4, so 2 times 4. We don't know dx/dt, but that's okay. This is what we're trying to solve for, so we'll leave it as an unknown. Plus 2. Well, we know dy dt is -2, but we don't know why. So this is a bit of a problem. Notice, we have this extra variable right here. This is not good. If we were going to rearrange and solve for dx/dt, well, we're going to have a y left over, and we need to plug in for the y. So over here we have a bit of a mini problem. We need to determine y. That's our little question. It's like a side problem. We need to determine y. Now, to determine y, we're asked basically, what is the height? What is the height of this ladder? And the height is always going to be changing. But we're looking at a particular instant in time. We're plugging in x equals 4 because we're going to be looking when the base is 4 meters from the wall, which means we can plug in that 4 into this equation here. 4 squared plus y squared equals 5 squared. And that will allow us to solve for y. So we get y squared equals 25 minus 16, or y squared equals 9, and y will equal 3. It's usually not too challenging to determine a missing variable in these questions. You often go back to the original equation you wrote down, and maybe you plug in some numbers to find the missing quantity. So now that we have that y equals to 3, we can go ahead and plug it on into the equation. So let's keep on trucking. We're going to get 2 times 4, which will be 8 dx dt, plus 2 times 3 times -2 equals 0. Or 8 dx dt is equal to, when you move that to the other side, it's going to become a positive 2 times 2 times 3, so 12. And you can divide both sides by 8, so dx dt is equal to 12 over 8, which, make sure you simplify, will be 3 over 2. Finally, step 7, we can answer in words. So 7, the base is moving away at a rate of 3 over 2 meters per second. And we solved our problem. Now, as we do these questions for related rates, we're going to need some different formulas. The first one required Pythagoras' theorem, and hopefully you knew that theorem or that formula. But there are many other formulas in math, and we're going to need all of them at our disposal. So here are a few multiple choice questions to try to review your formula knowledge. The first one, what's the volume of a sphere? Does anyone remember the volume of a sphere? Is it pi r squared, 4 pi r squared, pi r cubed, 4/3 pi r cubed? Hard to say. I'll give you a minute to think about it. Take your best guess. Alright, so the volume of a sphere is 4/3 pi r cubed. So just to help explain this formula a little bit, we're looking for volume. And volume means you're going to have 3 pieces, right? If you think about volume, it's in 3 dimensions. So it makes sense that you would have a cube here because there would be three pieces that need to be multiplied to get your third dimension. So it can't be A and B, it's got to be either C or D. And in fact, the 4/3 is a very famous result. It took a lot of mathematicians a long time to figure out this, but once they did, the pi makes sense, of course. It's a sphere, it's based on circles, so there'd be a pi, and the 4/3 is that weird fraction that goes in front to get the volume. Now, what about the volume of a cone? Any ideas on the volume of a cone? Feel free to pause the video, take a guess at it, and then we'll go through it. Alright, well the answer for this one is B. Now, you might have been saying, wait, isn't it cubed? Isn't it volume? Well, there's supposed to be 3 quantities being multiplied together to give volume. 3 variables, not a pi. Pi doesn't count as one of the quantities to make 3 dimensions. And so, if you look at r cubed times h, that's actually going to be 4 dimensions. 4D. We're not in 4 dimensions, we're in 3. So the answer is going to be B with the r squared h. In fact, if you want to think about the volume of a cone, A cone looks like this. And so the bottom is a circle. Does everybody remember the formula for the area of a circle? Hopefully you do. The area is pi r squared. And so a cone is like a circle that's been stretched up a height h, but it's also been made into a bit of a triangle. And how many sides does a triangle have? 1, 2, 3. So you've got to divide by 1/3. Now, that's not the actual reason for the formula, but it might help you remember it a little bit. You have the area of a circle right here, you have a height of h over here, and you have a 1/3 because of a triangle. How about the volume of a cylinder? Pause the video, take a guess, and then we'll look at the answer. Okay, so the answer for this one is C. This one actually can be understood as a picture. If you draw your cylinder, the area here is going to be pi r squared, and then its height h. You can think of this as though the circle has been stacked over and over and over. There's a bunch of circles that are stacked all the way up this cylinder, and there's in fact h of them. So it's pi r squared times h. Pi r squared for the circles, and then h all the way up. What about the volume of a box? The volume of a box. Well, if we were to draw ourselves a box, it's a little tricky in 3D. A box would have 3 dimensions, x and y and z. And for a box, you simply multiply all 3 together. So the answer is A. Now what about some surface area questions? What's the surface area of a sphere? Well, the surface area of a sphere is going to be 4 pi r squared. 4 pi r squared. Now that's again a tricky formula to remember, but there's a bit of a weird trick here. If you remember the volume of a sphere, it's 4/3 pi r cubed. And if you were to take the derivative just for fun, the 3 would come down and would cancel. So you'd have 4 pi r squared, which is the formula for surface area. Now, this only works on the sphere. It's a weird calculus thing that I'm not going to prove for you here, but it only works on the sphere, but it is a memory trick for remembering the surface area of a sphere. What is the surface area of a cylinder? Please don't try some weird derivative trick. See if you can remember from grade 10, what is the surface area of a cylinder? Alright, the answer I'm going to derive for you before I circle it. If we draw a cylinder, we see that a cylinder has a top and a bottom, and then it's got this portion that goes around. Well, the top and the bottom are both circles, so they were going to have area, pi r squared, and so we're going to get a 2 pi r squared, which starts to lean towards maybe formula C or formula D. Now the area around a cylinder, you can think of unrolling that as a big long rectangle. It's going to have height h, and the length along the bottom of that rectangle is actually coming from the circumference of the circle. Hopefully you remember the circumference of a circle is 2 pi r, which gives the area of that rectangle as 2 pi r h. So our final answer, if we combine all of these together, is 2 pi r squared plus 2 pi r h. Alright, now that we've reviewed a bunch of our formulas for surface areas and volumes, let's go ahead and try a related rates question. A gas is escaping from a spherical balloon at a rate of 10 cubic feet per hour. At what rate is the radius of the balloon changing when the volume is 400 feet cubed? Well, let's start with step 1. Let's try to draw ourselves some type of picture. So we have a spherical balloon, so some type of sphere here. It's a little hard to draw a 3-dimensional sphere, but you get the picture. And we need to label this. We need to give it some type of label, and whenever you're drawing a shape, give it the labels that make sense. Spheres are defined by their radius. A radius is very important for a sphere. So, we'll give it R for radius. Maybe I'll put that above right here. R for radius. And that's the only thing you need to label. Sure, you could label extra things on the sphere. You could label diameter, which is 2r, but don't go ahead and introduce extra variables if you don't need them. Just label it with the radius. All right, what are we looking for? What are we looking for in this question? At what rate is the radius of the balloon changing? Oh, we're looking for dr dt. Okay, what are we given? What information are we given? Oh, we're told that gas is escaping. What that means is this balloon is shrinking. It's getting smaller and smaller. Gas is escaping. Well, what does gas relate to in a balloon? Does that relate to its radius? Not directly. Does it relate to the surface area? I don't think so. Gas relates to the volume of a sphere. As gas leaves the balloon, it's going to have less volume. And so dV dt is given to us because it's told that gas is escaping at a rate of 10 cubic feet per hour. So negative 10, because it's decreasing, feet cubed per hour. Okay, so we've been given that. We're also, of course, given the volume. So we're given the volume as 400 feet cubed. Now we need to combine all this information in some type of equation because we need to take a derivative. Well, the most obvious equation to start with would be the volume of a sphere. We're talking about volume. Maybe we could write down the volume formula. Hopefully you remember this formula. Take a guess. Okay, the volume formula is 4 over 3 pi r cubed. Well, we can go ahead and do a derivative. dV dt equals 4/3, because it's a constant, and the pi is a constant too, times 3r squared. And then we need to put a dr dt. Now, we definitely want to simplify these as we go, so the 3's can cancel. And so our formula will be a little bit nicer. We'd have dV dt equals 4 pi r squared dr dt. We want to start plugging in the information we have. So it looks like we can plug in most of it. If we look here, we know the volume is 400, so we could plug that in. Although there is no v in this formula, so okay, we don't need to plug that in. We have dV dt, though, is negative 10, so we could plug that in on the left-hand side, negative 10. But I don't see r anywhere. I don't see us having r equals in any of our work, which means we have a little mini problem. Over here, we need to determine r. Well, again, we tend to use our initial equation. So we know that v is equal to 4/3 pi r cubed. So 400 equals 4 over 3 pi r cubed. And we can definitely use that to solve for r. So let's go ahead and work on that here. We want to determine r. So we could multiply both sides by 3, divide by 4. So we're going to get 400 times 3 divided by 4 equals pi r cubed. The 4 and the 400 can reduce to 100 times 3 equals pi r cubed. So we'd have 300 we can divide by pi. And then we should probably cube root. So r equals the cube root of 300 over pi. Not a nice number, but we were able to determine r. Now let's go back and see what we have in our equation. We have dV dt equals 4 pi r squared dr dt. And what are we looking for? Well, we're looking for dr dt. I tend to isolate first. It's up to you how you want to do this, but I'm looking for dr dt, and I'm going to solve that before I plug in. I think it'll be a little bit nicer. So I would write that as dr dt is equal to dv dt divided by 4 pi r squared. So we can start plugging in the information that we have. We know that dv dt is negative 10 over 4 pi. R is equal to this terrible cube root, so we'll put that in. The cube root of 300 over pi squared. And we should try to simplify that a little bit. Well, the 10 over 4 could simplify as a 5 over 2, but that's about all I can do. Maybe I could rewrite this power in the bottom, so I'll have negative 5 over 2 pi, and I guess I could write this as 300 over pi to the 2 over 3. But I certainly can't do the 2 over 3 power of 300 over pi. There's no way to simplify that, and so this here would be our answer for r. So we just need to answer in words and we're going to be complete. The radius is, well, notice it's negative. I'm going to put that in another color. It's negative. So the radius is decreasing. Decreasing at a rate of, well, 5 over 2 pi, 300 over pi to the 2 over 3 feet per hour. Now be careful here. If you say the radius is decreasing, and you were to write this as a negative 5, you're saying it's decreasing at a negative rate. If you're decreasing at a negative rate, you're actually increasing. So be careful. If you choose to include the word decreasing, that already accounts for the negative sign, and so you don't need to then put another negative in your answer. Also, make sure that you include units and make sure they're proper. Radius is going to be just measured in feet, so that's why you put feet per hour instead of maybe feet cubed per hour. Let's go ahead and try another ladder problem. In this case, we have a 10-meter long ladder and it leans against a vertical wall. If the foot of the ladder is moving away from the wall at a rate of 2 meters per second, find the rate of change of the angle between the ladder and the floor when the foot of the ladder is 6 meters from the wall. So, same idea, we'll draw ourselves a picture. We know the ladder is 10 meters. Now, we could label X and Y. There'd be nothing wrong with that. So we'll label X and Y. But if you notice, when we go to say what's our rate we're looking for, what is our d something dt, we're looking for the rate of change between the ladder and the ground in terms of an angle. We're looking for an angle. The angle between the ladder and the ground would be here, theta. So we're actually looking for d theta dt, not dx dt or dy dt. This is our rate that we're trying to find, our unknown rate. Now, what are we given? Well, we're told the ladder is moving away from the wall at a rate of 2 meters per second. That means dx dt is equal to 2 meters per second. And we're told eventually that the foot of the ladder is 6 meters from the wall, so that means x will be equal to 6. Now let's go ahead and try to solve this problem. Well, we need some type of equation. And you might say, oh, Pythagoras, right? X squared plus y squared equals 10 squared. And that is true. And if we do the derivative, we'd get 2x dx dt plus 2y dy dt equals 0. But notice, we want d theta dt, and nowhere here do we have a d theta dt. This will not allow us to find our missing rate because there's no theta in the equation. So this is no good. This does not help us. We need a different equation. So think about it a little bit. What equations do you know? Is there an equation that relates theta? Do we somehow know something about theta in terms of a triangle? Is there a SOHCAHTOA? And if you think long and hard, you should find that we have sine or cos or tan. I'm going to use cos, but you could use any of them. I'm going to say cos of theta is equal to adjacent over hypotenuse. Now, you could use any of them. You could use sine, you could use cos, you could use tan, and I'm going to use cos for a very specific reason. If you notice, we're given information about x, which is the adjacent, and the hypotenuse is just a straight number 10. If I was to use, let's say, tan, I would have to find y later on. I'd have to find different values, and I don't really want to right now. I would like to keep everything in terms of x, because I have dx dt and an x value, and in terms of the 10, because the 10 is already there. So let's go ahead and find our derivative. Derivative of cos is minus sine, and then we do d theta dt. The x over 10 is not a quotient rule. The 10 on the bottom is just a constant, so 1 over 10. And then the derivative of x is dx dt. Now, we're good to sub in for the dx dt. We know that's 2. And we're trying to find d theta dt, but what is this? Sine theta. How in the world do I find sine theta? I guess I'm going to need a little step over here, a little thing on the side to determine sine theta. Determine sine of theta. Now, it's not initially clear how to determine sine theta, because we have this equation here that relates to just cos of theta. So we need some way to find sine of theta. And there's lots of ways to think about it. One might be to just go back to the triangle and think about another ratio in terms of sine. We could make a new equation here. Nothing wrong with that. So our new equation might be sine theta equals opposite over hypotenuse. So y over 10. That will allow me to determine sine theta because I now have an equation for it. But now I've created a further problem for myself. I now have an equation in terms of y, and I need to find y. Need to find y. Sometimes this is how these problems go. You start one thing and you end up down a rabbit hole trying to find variables, trying to get the missing information. But to determine y, it's not too challenging, because if you remember this work that we crossed off over here, we do have a way to relate x and y and the number 10. So we know the number 6 goes in for x. And we have the number 10 already, and so we can find y using Pythagoras. You thought you were going to escape using Pythagoras? Pythagoras is just so handy. He comes in almost every question, it can seem. So here we have 6 squared plus y squared equals 10 squared. Let's go ahead and work that math. Y squared is going to equal 100 minus 36. Y squared is going to equal 64, so y equals 8. Which is then going to give us sine theta equals 8 over 10, which is simplified to 4 over 5. Okay, we were able to find our value for sine theta. We can take this and plug it in over here. We know our dx dt from the beginning as 2, and so let's go ahead and find d theta dt. So 4 over 5 with a negative, d theta dt is equal to 1 over 10 times 2. So we could cross multiply the 5, get negative 4 d theta dt equals 2 over 10 times 5. I'm going to simplify that first, so d theta dt equals 10 over 10, which is just 1. So we finally isolate for d theta dt, and we get 1 over negative 4, or negative 1 over 4. Now, the units are going to be a little bit complicated for this. They didn't tell us whether it was degrees or radians, but they did tell us it was per second. So if you look at this, we have the rate of change of the angle over time. So it's clearly per second. And if they don't give you an angle, we always assume that the angles are in radians. If the angles aren't specified, it's automatically radians. So the angle is changing at a rate of negative 1/4 rad per second. Let's write that down in a sentence. The angle is changing at a rate of negative 1/4 rad per second. Now, when I was doing this Pythagoras over here on the left-hand side, I was able to do it pretty quickly because 8 was a perfect square. And what you should know is that there are a few type of triangles that tend to work nicely. For example, the 3, 4, 5 triangle is always going to be 3, 4, 5 in nice whole numbers because 3 squared plus 4 squared equals 5 squared. You've hopefully heard of the 3, 4, 5 triangle. It's called a Pythagorean triple because it's whole numbers that work with Pythagoras' theorem. You could, though, double it up to make a 6, 8, 10 triangle. And so if you see 6 and 8 or 6 and 10 on the triangle, you're going to know right away, still solve the algebra, but you'll know right away the missing side because it's a 3, 4, 5 triangle or a 6, 8, 10. You could even do a 300, 400, 500 triangle. You can try on your calculator. If you type in 300 squared plus 400 squared, you'll get 500 squared. Now, there are an infinite number of Pythagorean triples, in fact, infinite number of whole number solutions for this. But the only ones you should know about right now are the 3, 4, 5 and their multiples. And there's one other one, 5, 12, and 13. You can actually try it. 5 squared will be 25. 12 squared is 144, and if you add those together, you're going to get 169, which is 13 squared. So kind of neat there to know about these Pythagorean triples. They help you in your problem solving just to notice whole numbers and sometimes solve for missing variables a little bit quicker. Now for homework, we have a few questions here. Go ahead and try these questions on your own, see how far you can get, and then go ahead and watch the videos. So there's videos explaining each one of these. Related rates video number 1 is here at tinyurl.com/relatedratesq1. And then we have another question over here, tinyurl.com/relatedratesq2. So make sure you give those a try and then watch the associated videos. And after that, we'll look tomorrow at some further related rates problems. Thanks for watching.